Hey guys, so this is my first ever video. I'm recording and publicly putting it out there. And yeah, so let's start it. So today we will start with linear regression. Okay, so now what is exactly linear regression? Linear regression is, in simple terms, if I would say, it is just a way to predict a number, okay, that is output based on other features or numbers. That is our inputs. That's it. Now, how do we do this? How do we define this statement? How do we achieve it? Okay. So, with the help of this, y is equals to mx plus. Okay. Most of us, we have seen this equation in our mathematics, right? During high school, it's a basic line equation. This is what it looks like. This is y, this is x, this is our slope m. That's it. This is like the this is what linear equation is. Okay. Now, how all of these things work? Okay. So, mm, see, we here have our graph. We have your y, we have your x, we have your m, and y is equals to mx plus c. We have the equation here. So let me break down every single thing. Y here is the output, the number we are trying to predict. Okay, that's it. Then X is the input, the data sets. Okay. C C is biasing. Okay, C's work is to just shift this line up and down. That's it. Like if we want to start our line from here, then we need to change the value of C. If we want to start from here, then we need to change the value of C. So that's all C does. It just shifts line up and down. That's it. Okay. The main thing here is the M, the slope. This is what like it's the brain. Okay. And in terms in machine learning, if we call this as weights or weight. Okay. The weight its work is to manipulate the input data. So here the input data we are considering X as input data, right? We are giving the input data the name as X. So weight job is to manipulate X in such a way that we will get our expected output Y. Like what we are expecting our model to do based on the specific input data we have given. So this M is what that handles the job. Okay. Now, how do we find the M here? How do we do it? Okay. You might say that it's simple. Like, suppose, let's consider a way. Suppose, let's say we have taken C as 0. Suppose, okay. Suppose we want to start from this neutral point. Okay, so we have supposed taken c is equals to 0. So technically the equation becomes y is equals to mx. C doesn't affect the equation that much. C just shifts the line. Okay. So what affects the equation is m. So you might say that, bro, it's easy. So we want to calculate m. M is equals to y by x. Yeah, it's simple. When we are dealing with normal numbers, okay, like suppose I am giving you that, bro, I have given you the input x is equals to 1 and I want y is equals to 2. In that case, yeah, it's simple. We can easily predict the slope. M is equals to y by x, so 2 by 1, that implies 2, so m is equals to 2. It's easy. But this is not the data kind of data we are dealing in AIML. Okay, this are simple numbers. This is not we're dealing with AIML. In AIML, we're dealing with matrices that has features. So there are two methods. First method is the inverse matrix transformation. Inverse matrix transformation. The second method is gradient descent. Gradient descent. Now let's break down these two things. So the first thing, inverse matrix transformation. Okay. So see, in AML, we don't deal with simple data structures. Okay. Our datas, they are 2D arrays. Okay. You know array, right? Simple plain data structure. Array or list 1, 2, 3, 4. It's a simple 1D array, right? But in AIML, we deal with vectors and matrices. So matrix are nothing but 2D data structure, 2D arrays or list, 2D arrays or list. Vectors is when we add features to our matrix. So this adding feature means adding meaning to our data. Okay. To our data. Without this, our data set, it would just be a simple 2D RM. That's it. No meaning, only numbers. Okay. No meaning in it, only numbers. If our data doesn't have the meaning, how do we know like what it is representing, what it's like, why it exists, right? So now let's talk about the input data and how inverse multiplier transformation works. Now, so let's take the house pricing calculation example. Okay, it's a very common example while teaching AIML to someone. So suppose I am asking you that, bro, I am going to buy a house that which that area is 1,000 square feet. Okay, the area of the house. Now my question is, what will be its price? Like not exact price, but what can we expect? What can we expect? Like our expected price. Okay. So how do we do it? So see, before predicting this data, we are to train our model. Like, okay, so if suppose I'm asking you in a general manner, let's just forget about ML for a moment. I'm asking you. So suppose you said that in this area for 1,000 square feet, you can expect $100,000. So how are you telling? Is because you already have the data, like you know the pricing around there, you already have it in your brain, right? So you are kind of giving me an approximate value. It's not an exact value for the plot, but it can. Oh, it's like giving me an idea. Like it might be 110 while buying it, or it might be $90,000. But I don't know. Like, but 100 is just expected. It's like giving me an idea. So as you know the area, you know the place, you know the locality, you have already seen uh, people buying houses, selling houses, you already know. So you are telling me that, brother, you can expect this much price. So like that, we also need to tell our model, right? Like our model also needs to know that, yeah, this is the current scenario of this certain region and this is the expected price. So like that, our model also needs to learn the thing. So how do our model learns? Through machine learning, right? So what is happening is that for our model to learn the thing, we first need to give it a few input data. So linear regression, it is a supervised learning algorithm. Okay. There are two different kinds of algo. One is supervised, another one is unsupervised. Okay. So, right. But our current focus is supervised. This linear regression is supervised. So supervised, what happens is that we are giving our machine learning model input X, also the expected output Y. Okay. So you might say that, bro, if we're giving the input X and we are giving the expected output, okay, then why are we even training it? So let me tell you, see. So first we give sample data to our model, right? So few sample data. So suppose house number one, for example, 1,000 square feet, house number two, 2,000 square feet. Hmm. Like this is the input data X we are giving to our model, and this is the output data. We are defining expected output data for house number one. As per its area, the pricing will be around roughly around this much. For house number two, as per this area, the pricing will be around roughly this much. Right? So now what happens is that our model calculates the M, the slope, the weight. Okay. After doing the job, it gives us a predicted Y value, right? Then we compare this predicted Y value, the value given by our model, the output given by our model, with this expected value, the predefined value. Okay. And we calculate the error, how much the error is there or loss is there. Okay. Based on that, we then again retrain our model. Again. It happens in a loop. And then when we minimize this error value between the expected value or the genuine value that's been predefined by us and the predicted value, then we find the most optimized slope, right? After finding the most optimized slope, we then use it on new data to predict. Okay. So that is what its job is. Now, so like There are a lot of questions right now. The first question is why the data are in the matrix formats? Because and why do are they called as vectors? So suppose I gave you 1000, 2000, 3000. This is a 3 cross 1 matrix, right? Number of columns is 1, number of rows is 3. So 3 cross 1 matrix. Does it has any meaning when you look at it? You are like, no, this 1000, 2000, 3000 is a 3 cross 1 matrix. No, it doesn't has any meaning. How do we add meaning to it? We define this is house 1, this is house 2, this is house 3, and this is the area, and its unit is square foot. When we add the meaning to this data, it becomes a vector. That's it. How? Why in matrix format? Because we need to give our model a lot of informations. Okay, a lot of same type information, just like we do. So, see, if you just know that okay, one house whose area is this sold at suppose 90K, you won't be that efficient. But if you know 10 different houses and then you can kind of average their like have a proper good idea. Like, so the more amount of data, just like us humans, the more amount of data, the more amount of information we process, our output becomes better. The same with machine learning. And the most efficient way to do is using this matrix format. It's technically a 2D array. Okay. That's it. So now, so now let's get on to other two methods, the inverse matrix and the gradient descent. So in inverse matrix is simple. Y is equals to mx plus c. Let's just for a moment forget c. Okay. Y is equals to mx. And so m is equals to y by x. Now, as it is a supervised learning, we are giving our input to y. So suppose let's say this is what our data looks like 1000, 2000. This is what our input data is house 1, house 2, square foot area, right? This is how this is x, and suppose house 1 price is 90K, house 2 price is 30, suppose let's say it's 120K. Okay, this is y. Okay, so now we can write this as y into 1 by x, correct? So y, we will just directly put this matrix here to calculate. Now, here 1 by x means we can write it as this y into x inverse. So wait, this is matrix. This is not a plain number. We just cannot divide them like that, y by x. So here y into x inverse, right? We can calculate x inverse and we can have it. Now calculating the x inverse is a linear algebra concept. We don't have to worry about it that much because we have already Python libraries that does this jobs for us. But the thing is that this inverse matrix transformation, okay, even though it's like accurate, because it is accurate and it is just a one step thing, right? We just divide them. We just here the main job is to just calculate this inverse. That's it. That's all we have to do. And within one iteration, we will have our required M. The thing is that we don't opt for this method is that the inverse matrix calculation is very hardware heavy. Okay. So This inverse matrix calculation, its time complexity is of n cube, right? So n here is the number of features. What happens is that when the value of n it goes up, what happens is that at that time our calculation speed drops by a massive amount. Okay. Also, we don't even have that kind of like hardware resources to like properly do it. Therefore, we opt for gradient descent. So now, what is this gradient descent? Gradient derivative. If you have read calculus, you know what is derivative. Descent is a simple, like descent means going down, right? It's a simple. So finding a point on the graph, well, it's like it's like finding the most optimized point. Okay. So now, how do we do it? This, let us go through it. How do we do it? So here there are some key terms. One is weight or slope. N. Okay. But we'll be sticking with weight because that is what we call it in AIML weight. Okay, not slope N. Then comes the B, biasing. C in our equation. Okay. This thing is this, right? And this is this. Then we have the input x is equals to input. Hmm. Now there is another thing, learning rate. It makes sure we will go through it. What it is. It makes sure that the descent is this silence is not broadened. Okay. And then comes the iterations. Now we will go through. I will write a sample code and I will explain it on the side how it's working. So now, initially, for most part, we defined hollow state weight as this and biasing also this. For most part, we defined learning rate. We always take it a small value. Okay, learning rate. Then iterations depends. We can 1,000 is the most common one, and it's equals to ln of x. And we have our expected output y, expected output. Okay, y expect. Then we have our input x. Okay, input. So this is how it works. For I'm writing the code here for I in range of iterations, y prediction is equals to w into input plus biasing. Then we calculate dw is equals to 2 by n. Then summation of y is equals to 1 to n x into y prediction minus y expected. Okay. I know here you are going to get confused. I will explain. dw is equals to 2 by n into summation of say y equals to 1 to n y prediction minus y expected. Now here the weight updation happens. W is equals to W minus learning rate into dw. B is equals to B minus learning rate into dB. That's it. So now you might ask me that what is this? This C. So first what happens is that there is a thing called a concept cost function. Okay. So this is how the cost function looks like. Okay. Uh Let me read out this whole thing. Yeah. So let us go to the cost function again. So this is what the cost function looks like. Okay. So the gradient descent concept, it works on the basis of we start at a random point on the graph. So this point we see, this bottom point is the most optimized point. This is our goal. Okay. This is where we want to reach. So when the slope value is this, the weight value is this, is the most uh, optimized value. Okay. Now, it's not like we always directly start from here. Okay. We always take a like random W. In our case, we have started at 0.0. Suppose in this graph, when we're starting, suppose initially our W lies. Now we eventually go to here, right? Like from here to here, then from here to here, then from again maybe here, then here, then here. Like this, we eventually reach here. Not exactly here, but somewhere near here, like here or here. This is what the iteration helps us achieve. Okay, this is where the iteration comes into play. The more number of iterations we have, the better our W, the weight is, the much, right? So if we are running our iteration, suppose we are making it, currently we have 1,000. So suppose we make it 10,000, w- then literally we will be running in this cost function 10,000 times. So obviously we will reach a much more better place than we can reach with just 1,000 iterations. Then comes this is our linear regression, right? Y is equals to Wx plus B, linear regression. Now we predict some sort of values, but it's not the perfect value. Okay, why? Not in the first go. So suppose in our data set we have a 1,000 square feet house and is in the expected output, we have defined its price to be 1,000. Okay, sorry, 100,000. But our model predicted this 1,000 square feet house to be suppose 50,000. Okay, is it matching with it? No, it's a huge amount of loss or error, right? So it means we need to update our weight. How do we do it? This is how we do it. DW. Here chain rule and our normal. Here the chain rule, product rule of the calculus is used. So I am going to explain it here, but if you don't know calculus properly, then it is going to be trouble for like you won't be able to understand. So you can skip this part. But if you have an idea about calculus and you want to know how we are arriving at this equation here, so you can stick to it. Now, dw is equals to 2 by n into summation of is equals to 1 to n x into y prediction minus y expected. Now, let's go through this thing, how it is happening. Okay. So, see, first, what do we do? Like, uh, if you know chain rule, then what do we do first? First, we assume a weight W, we apply it on our input X, we get our Y prediction value after doing that, and then getting the Y prediction value, we then calculate the difference between then like the this is what is error, then we calculate the error. After calculating the error, we calculate the mean square error. Okay, so right, mean square error formula is 1 by n into error square, right? What do we want to reduce? We want to reduce this. How do we do it? N is the length of the data set because mean square error, right? We are averaging here, so we need to divide by n. So this is the formula for mean square error, right? Simple mathematics here. So our goal is to reduce this thing. How do we do it? So how do we do it? So we do it by using our derivative. Okay. So let's go through it. So first, how do means our main target is to reduce this, and how can we reduce this? Now by changing our W, right? So W is the only thing that's affecting our output, like this our overall output, that which in turn is affecting this error value, right? So how do we start it? First, we derive and first we differentiate d of MSC by d of error, right? Our main here motto is d by MSC by dw. This is what we want to reach. So how do we start? We started by like this. So d of MSE, we have our formula 1 by n. So 1 by n is going to get out, then 2. So like it's a constant 2 will come out, then we will have here error, right? Now, now the next step is d now 2 by n, it will come out. Now our next target is d of error by d of vibrate. Here is the tricky part. You might ask me that, brother, error is y prediction minus y expected, right? So why we are doing only y prediction here? Why we're differentiating it? Because y expected is already predefined. It's like a constant thing. We have defined y prediction, right? For the certain amount of input x, this is what the expected value should look like. So it's a constant. Y expected is a constant. So constant it is going to be one. No changes. This is what that is going to get affected, the prediction. So we can ignore this for the time being. Okay. Now, what causes Y prediction? What causes Y prediction? Mx plus C or Wx plus C, right? Correct. So D of Y prediction by D of W. So that's it. And we finally reach our input X, right? So D of Y prediction is D of, because see, let me write it. D of prediction is equals to how it's working by dw. So B of prediction would be Wx by dw, right? So X, correct. So now let's move on to the, like, now I will write this thing properly. Touch the proper channel. D of n is E by dw is equals to 2 by n, correct? Then into our error into X, correct? So now 2 by n, what is our error? Y prediction minus Y expected and X, right? So see, suppose we have three different house prices. House 1, 1,000 square foot. House 2, 2,000. House 3,000. We have three different house pricing, right? So for each house pricing, we will apply W and we will get a Y prediction value for each thing, right? This is Y prediction for house 1, Y prediction for house 2, Y prediction for house 3, correct? So all of these things, they will have their own prediction values. So if so, like, to calculate the whole of DW that we are to be changing, how do we do it? We just add them up, right? So for house 1 plus house 2 plus house 3, correct? 2 by n is a common term in every single thing, so we can take 2 by n common. So what leaves now? Summation for just I is equals to 1 to n of what? Y prediction minus Y expected multiplication of input value. That's all there is. Correct? So this is how the equation works. That's it. Okay. Now, like, why we need it? Why we use linear regression? Because it is simple. First thing, it's simple, right? It's a simple thing. Uh, it is genuinely a simple thing. If you know, like, if you still have doubts, like I'm not understanding and all, then first thing is for you to clear our concepts in linear algebra. Then in calculus, you don't have to do like rocket science level study. No, no, no. Just know the, like, what this topic mean, and it's, you will be like, literally linear regression will, like, it will click you within like 15-20 minutes. That's all it takes. Okay. Now it's a simple. It is first, like, uh, for small data sets, we can use inverse transformation, right? and we know it's a one-liner thing. So it is going to be a simple thing, right? Easy, efficient. And even if we use gradient method for last data set, still it's a simple thing because yeah, like once we find out the weight, then we like it is first because all we have to do is input data. We have to like get the input data and we just have to multiply W with it and the resultant answer is Y. Done. That's it. So, and also it handles a lot of problems easy. Okay. Like in finance, stop predicting. Okay. It handles easily. And also in healthcare, sports, healthcare, business, in business, for ads. Okay. Then sales, like in business, ads and sales, like how, like based on ads, based on a specific ad who has a number of sales we can expect or something like that. Okay. So like this, there are a lot of things. But the thing is that there are a lot of limitations to this linear regression, which is why polynomial regression exists. Okay. That's the reason why polynomial regression exists. So, like, for example, the first thing is that uh, linear regression, it assumes a linear relationship. We can see here, so a straight line. But in reality, this is not how the real data works. Like, for example, for stock predicting, or even if healthcare or so, or the business, like based on ads, expected sales, or something like this. These things, brother, they are not simple. Okay, we just cannot draw a line on it and we can predict it. No, 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 no. It's wrong. This thing, they are curve. We need curves around like this or this, something like this. Hmm? This is this is the first problem it has. So fitting every single data point on a single line is actually a very wrong idea. That's the first thing. And it is very sensitive to outliers. Like, for example, we are having normal data, 1000 square feet, 100K, 2000 square feet, 200K. Even though these are not the same data, but they lie in the same group. Like, we can consider them as the same group kind of thing. But suppose, let's say, uh, something weird thing happened. Like, for example, 2 lakh square foot, and its price is just 100K, for example. I'm saying, nah, it's outlier kind of thing, right? It's like, so linear regression won't be able to properly predict it. So there are overfitting and underfitting issues, right? So overfitting is when the linear regression models learns too much that it also takes up the noise with it. Then this overfitting happens. Like, see, for example, like I said, in AIML, to know AIML, you know the basics of calculus and linear algebra and probability and statistics, which at maximum will take you to 2 months, max 2 months. Okay. But if you sat down and study like a rocket scientist or a NASA scientist or SpaceX scientist, then it's good to know because these are very advanced knowledge and like we need people best who knows these things and slop and can solve this complex situation. But is it really needed for AIML? Like that is what our target is, right? So it's like we are kind of deviating from our target, right? We are forgetting our goal, right? S- Correct. If it's good to know a lot of things, but at the same time, we're forgetting what our end goal was. So this is one of the issues. It can easily overfit, and underfit means uh skipping things. Okay, like learning a few topics only. Okay, skipping things, not learning properly. Okay, just having a basic idea, like something like that. Okay, that is what underfitting means. So we use a regularization algorithm to fix this thing. Okay, there are a lot of regularization algorithms, L1 and L2. We use them to fix this thing. Okay. And this L1 and L2 regularization, they are a separate topic on their own. So like explaining those things in this thing will make it very lengthy. So yeah. And this is for now. And I hope you understand every single thing till now. I will also attach a sample code on the description so you can check it out. And yeah, thank you for like giving it a try. This is my first time. Okay. So I know there are a lot of, it's not a perfect video. It's like there are a lot of mistakes here and there. But yeah, it's like, it will be good with time. So yeah, goodbye.